So these three problems continues into the same idea of uh, approximations of a measurable function by either simple or step. Before we saw the simple functions, approximation with simple functions, and now we're going to look at approximations by step functions. Okay? So so what's the difference, first of all, between simple function and step function? Okay, so keep in mind f is not f, sorry. Let us just recall everything. So f function phi is defined on a measurable set E into R. So you have phi is said to be simple if phi is equal to sigma of AI's key of EI's, where EI's are measurable sets. Okay, and it is said to be step function, simple function, step function, if phi is equal to sigma of AI with key of n. Okay, so this is where INs are intervals. So either your function is a linear combination of characteristic functions of on measurable sets, okay, disjoint measurable sets, or on disjoint what? Intervals. Okay, so this is the difference between step function and simple function. Okay, the step functions, they play a major role in the Riemann integral, while the simple functions play a major role in the Lebesgue measure. In any case, so problem 1. So we have E, which is a measurable subset of I. Measurable. Okay? So we fix epsilon positive. Okay? And we want to build a step function on I. Okay? Which coincide with the characteristic function on a subset f of I, which almost gives me the measure of. So first what we are going to do is measure phi, of course. That's what I meant. So here we're going to use the fact that there exists. So we know from the theory of measurable sets that for this epsilon there exists an open subset, such that E is in O and the measure of O minus E is less than epsilon. I mean, we may have to do epsilon over 2, but again, as I always said, it doesn't matter. So at the end, if you have 2 epsilon, it makes no difference whatsoever, okay? So anyway, so now what happened? So what we want is, it's easy to see. Right? Note that the measure of O is going to be equal to the measure, because O is open and is measurable, therefore we have the measure of O minus E plus the measure of E, okay? And since the measure of E is finite, because I is a bounded interval, so this will be less than epsilon plus the measure of E, which is finite. So you see the measure of E, the measure of the open set is finite. In any case, since it is an open subset of R, so your O is equal to the union of disjoint, okay, from 1 to infinity, disjoint intervals. Disjoint open interval. This is beautiful result. Okay, any open subset of R is a countable union of disjoint open intervals. Since the measure of O is finite, so we know that the measure of O is going to be sigma of the measure of all the INs. I'm sorry, INs. And since this one is finite, okay, for that epsilon, okay, so there exists n such that the remainder of the series In from n plus 1 to infinity is going to be less than epsilon. Okay? So now we take O star to be the union of In from 1 to n. Okay? And let us denote the complement by in O. Huh? So by O star bar, which is O minus O star, which means that this one is just the union of the INs from n plus 1 to infinity. Okay, so now what do we have? We have E, which is a subset of O. So it's going to be E intersect O star union E intersect its complement in O. Okay, so the measure of E is going to be the measure of E intersect O star plus the measure of E intersect O star bar. But the measure of E intersect O star bar, this is less or equal than the measure of O star bar, which is equal to sigma of the measure of In from n plus 1 to infinity, which is less than epsilon. So this tells me that the measure of E intersect O star, so this is greater than the measure of E minus epsilon. Okay? Great. So now let F, the subset we are looking for, which is E intersect O star union I minus, because we want to stay in I. Okay, so we add I minus O. So now if we take, so we claim, in fact, that I minus F, because F is a subset of I, is included in O minus E intersect O star. So indeed, let X belongs to I minus F. So X belongs to I and X does not belongs to F. Okay? So I claim that we have X belongs to O. Otherwise, if X does not belongs to O, okay, then X belongs to I and X does not belongs to O. In other words, we have X belongs to I minus O, which is a subset of F. A contradiction because we said X doesn't belong to F. Therefore, X belongs to O. Good. And obviously, since X does not belong to F, X does not belong to the first part of F, which is E intersect O star. So X belongs to O minus E intersect O star. Okay. So we proved the inclusion, therefore, so the measure of I minus F is going to be less than the measure of O minus E intersect O star, which is equal, because here everything is measurable. These sets are all measurable. O is open, so it's Brilliant, so it's measurable. minus the measure of E intersect O star. And remember that the measure of E intersect O star was bigger. So this is less than the measure of O, measure of E plus epsilon. Okay? And again, so what is this? This is O minus E plus epsilon. And the measure of O minus E, by definition, the way we build it, the open set, is less than epsilon plus epsilon equal to epsilon. So if it is a problem, so what you do, you go back and instead of starting, so here you can right here, you can replace this one by epsilon over 2, and here by epsilon over 2 to have here epsilon instead of epsilon over 2. So we build this f. So this is just, once you are done with the proof, then you know how to divide and by how much you divide. So anyway, so we found this set f subset of I such that. Okay, so now I need to find the step function because so what is the step function that we are gonna consider here? So set h to be sigma of key of every in from, so these are the characteristic functions of these intervals in's from 1 to n. Okay, which basically is just the characteristic function of O star. Okay, so it is a step function. The in's are disjoint intervals. So in here, if x belongs to f, so what do we have? So we have x belongs to E intersect O star, or x belongs to I minus O. Okay, so what's going on is that if x belongs to E intersect O star, we're going to have x belongs to E, and so if, so this is case 1, if x, sorry, if x, so we have 1. First case, if x belongs to E intersect O star, then x belongs to E and x belongs to O star. Okay, so h, sorry, not h, yeah, h of x, which is key of O star of x, is going to be 1. Okay, and the characteristic function of E of x is also equal to 1 because x belongs to E. So we have, so h is equal to key of E, in this case, sorry, of x. Good. So the second case, if x belongs to I minus O. So x does not belongs to O. So that clearly this implies, so x does not belongs to E and x does not belongs to O star. So we have key E of x is equal to 0, equal to key of O star equals of x, equals to h of x. So for every x in f, we proved that h of x is equal to key E of x. And that is exactly what we were asked to prove. Okay, so this completes the proof of the first one. It was long, beautiful construction. Okay, now we go for the second one. So we have psi, which is defined on I, which is simple function. So what we're going to do, we're going to use, so we know that psi is measurable. Simple functions are measurable. Okay, and take E to be I. Okay, So we're going to use 1. Use 1. Okay. So there exists for every epsilon. Okay. There exists f subset of I. Yeah. Such that and h defined on I. Okay. Such that the measure of I minus f is less than epsilon, and h restricted to f is equal to c restricted to f. Okay? So that proves problem number 2. So again, you start with a simple function. Almost you found on the entire interval I a step function such that they are equal. So it's almost, not on the entire set, but up to epsilon. Okay? 3. Okay? So now, what we are going to do is start with, so we have f, let f goes from I to R, which is bounded and measurable. Okay? So we know if you fix epsilon arbitrary positive, there exists a simple function, okay, from I to R, simple function. We have seen this before when we did the approximation by simple functions, such that the sup of over the entire interval I of phi of x minus f of x is less than epsilon. Okay, so we have done that before. This is an approximation of a bounded measurable function by simple function. So now we can use the question just before. So there exists now for that epsilon. So there exists f subset of I such that the measure of I minus f is less than epsilon. Okay, there exists also step function h defined on I, step function now, okay, such that h restricted to f is equal to phi restricted to f, right? So now what do we have? We have the sup over f. Let me rewrite this slowly. Sup when x belongs to f of h minus f, yeah? So this is going to be less or equal, sorry, it is equal first. So this is equal to the sup of phi minus f. I need to put x here. Phi of x minus f of x when x belongs to f. Why? Because phi and h they coincide on f, okay? And this is less than the sup of phi of x minus f of x over the entire interval I, which is less than epsilon, which proves exactly what we want.